Greetings to you. Myself Dr. Karuppuswamy, Professor and Head, Department of Mechanical Engineering of Sri Ramakrishna Engineering College, Coimbatore. Happy to welcome you for a brief session on metal joining process. Metal joining process is one of the important manufacturing processes in engineering field. The metal joining process is used to join two similar or dissimilar metals and alloys for the required applications. Today let us see what are all the important aspects of the metal joining process, classification of the metal joining process, and let us solve one or two problems in the fusion welding process. Metal joining process, the welding is a process of joining two similar or dissimilar metals by fusion with or without the application of the pressure and with or without the use of filler metal. This is the definition given by the American Welding Society. The key terms in this definition are, we can say there is a fusion. Fusion means melting and joining together the base metals. The base metals may be similar or dissimilar. And another important term is with or without the application of the pressure. Certain processes use only the fusion, and certain other processes they apply pressure for the joining of the two base metals. And one more thing is, we can use the filler metal or without the use of filler metal. So with this definition we can understand that there is a fusion of the similar or dissimilar metals with the two conditions. There may be application of a pressure or may not be application of the pressure, and we can use the filler metal or not using the filler metal. So these are all the important terms in the definition of the welding as per the AWS. And now let us see the classification of the welding process. The broad classification of the welding process: fusion welding, the first kind is, we can say, the fusion welding. As already we have discussed, fusion welding involves the melting of the base metal and joining together. So definitely there is an application of a heat and melting of the base metal will happen in that. We are using different sources of heat as defined here: arc welding, gas welding, thermite. These are all the varieties of heat sources. Among the arc welding, we have different sources of heat which gives a arc that will supply a heat to the base metal, and again a lot of varieties under that in the arc welding process and a metal arc welding process. This is one of the broad categories in the welding process. Second one, the electrical resistance. In this, the flow of electric current is obstructed. The obstruction will be converted into a heat energy. That heat is used to join the metals. We can say there is a resistance butt welding, there is a flash welding. One of the important electric resistance welding is a spot welding. We can very widely see in the automotive welding. Seam welding, there is another type of resistance welding is seam welding. It's just like making a continuous weld in that. Again there will be a projection welding like that. A lot of varieties are there in the electric welding. And the third major category of the welding process or metal joining process, we can say, in this the base metal is not melted but heated to a certain temperature, and we are applying the pressure also for making the joint. So one or two examples we can see. There is a friction welding, application of the friction, and we have to apply the pressure. Similarly, the friction stir welding we can see. Use of ultrasonics and many other varieties are there in the solid phase. There is a brace welding and there is a bracing. What is the difference between these two? When we see the bracing process, the capillary action is predominant, and that helps for the joining of the two similar or dissimilar metals in the bracing. Whereas in the brace welding, deposition of the filler metal will be there in the brace welding. and other two are the cutting and spraying. It is out of our scope. This is about the overall classification of the welding process. Let us see the fusion welding process. We have seen the classification of the welding. Varieties of welding methods are there, welding processes are there. Today let us see about what is the fusion welding process. In the fusion welding process, we are having a basic device. Let us say it's a transformer. We can see the transformer here. It is a welding machine, and there is a power output. One terminal can be a negative terminal, another can be a positive terminal, and there is an electrode holder here, and using that electrode holder, electrode is held and arc is generated at the workpiece, and one more terminal is connected to the workpiece. This is a simple arrangement in the fusion welding process. As already we have seen, fusion welding involves melting of the base metal and there is a joining together upon the cooling. So this is the basic about the fusion welding process. We can see that there is a, in this particular example, the source of the power is DC power source. So negative terminal will be there and positive terminal will be there, and the machine is having an option to convert or to position the power, either it is a DC or it may be a AC. Like that we can switch over between the powers according to our requirements. So when the terminal is connected to the positive, we can say that 2/3 of the heat will be going to the terminal. Here it is the workpiece which is connected to the positive terminal. So the 2/3 of the heat generated from the power source is going to the workpiece, whereas 1/3 of the power will be going to the electrode. So the whether electrode or workpiece connected to the positive terminal will generate 2/3 of the power. Today let us see one or two simple problems in the fusion welding process for better understanding, or how to select the welding machine for completing the welding process. The problem states that a direct current welding machine with a linear power source characteristics provide open circuit voltage of 80 voltage and short circuit current of 800 amperes. During the welding machine, the measured arc current is 500 ampere corresponding to the arc length of 5 millimeter. The measured arc current is 460 amperes corresponding to an arc length of 7 millimeter. The linear voltage E and arc length L, the characteristics of the welding arc can be given as E is in the volt and L is in the millimeter. This is the problem given. The objective is find out the relationship between the linear voltage E and arc length. So that is asked. Before that, we have to see what are all the characteristics of the fusion welding process. Let us say it is a graph. Horizontal, it is current. Let us say it is in amperes, and vertical, it is in the voltage. It is in the voltage. Now the characteristic is, let us say this is the performance characteristics or the relationship between the voltage and the current. So this voltage, the maximum voltage is known as a open circuit voltage OCV, and corresponding the intersection of the current in the horizontal axis is called short circuit current. This is the relationship. Normally, suppose for a condition voltage, it is the initial voltage, let us say V1, then the corresponding value of I is, let us say this is I1. Now the voltage is reduced. For example, let us say this is V2 and the corresponding current is I2. So the relationship is like this. It is called a drooping characteristics. There are two types of current and voltage. Let us see CC, constant current method, and constant voltage method. These are all the two types of setting we use for welding process. Constant current in the sense the percentage change of current is less than the percentage change of voltage. Let us say there is a V1 and V2 and similarly corresponding I1, I2. Suppose I1 minus I2 divided by I1. Similarly, V1 minus V2 divided by V1. If the percentage change of voltage is greater and percentage change of current is lesser, then we can say that it is a constant current type. In the opposite, if the percentage change of voltage is more than the percentage change of current, then it is termed as a CV. Okay, next question is when to use CC and when to use CV. Normally, the CC is preferred for the welding process done by the manually. So, welding process can be done in three different modes. One is completely manual process. Second one, semi-automatic, and the third one, fully automatic. For example, shielded metal arc welding, we can say that it is a manual welding process in which the operator has to handle the electrode and he has to perform the welding process manually. So, there is no possibility for making it semi-automatic or fully automatic. Due to the manual operation, there is a possibility for change in the electrode arc length, because of that the voltage will also change. So, the change in current will influence the welding process. So, as far as possible, we have to maintain the current unchanged so that welding bead will be uniform, thickness of the welding will be uniform. So, we have to go for constant current method for the manual processing. Whereas in semi-automatic and fully automatic, the intervention of the manpower is limited. Either the welding speed can be automated by using the table arrangement and servo systems, or as in the case of MIG welding process, the filler metal is continuously fed, that is automatic. So, we have to feed that filler metal automatic. Hence, at that time we can go for constant voltage process. Let us come to the problem. So, in this process, let us see the characteristic curve. Let us mention the details given. Open circuit voltage is 80 voltage. Short circuit current is 800 ampere. We have to recall the two equations of voltage. Let us say V equal to A plus BL, whereas V equal to EMF, then A and B are the constants, L is arc length. The relationship between the arc length and voltage, we can say it is like this, whereas this is L and this is V. So, let us say this is A and the equation is V equal to A plus BL. So, whenever arc length increases, voltage is also increases proportionately. This is the relationship between the voltage and the arc length. Similarly, there is another equation. Let us say X by A plus Y by B equal to 1. It is the equation for a given line. We can say that X is the current and this is voltage. Let us say I divided by IS short circuit current plus V divided by open circuit voltage equal to 1. So this is the another equation, we can use it. The first equation is voltage equal to A plus BL, the relationship between the voltage and the arc length. Here the second one is the relationship between the current, voltage and also the short circuit current and open circuit voltage. Okay, let us come to the problem. $80 volt open circuit voltage and 800 short circuit current. The arc length is given. For example, let us say during the welding machine, the measured arc is 500 ampere corresponding to the arc length of 5 millimeter. L1 equal to 5 millimeter, L2 equal to 7 millimeter. The corresponding current is 500 ampere and 460 ampere. Now let us substitute these values in the first equation. We can say V equal to A plus BL. Okay, so for example, V1 equal to A plus 5B. Let us say this is equation 1. Similarly, V2 equal to A plus 7B. That is the equation 2. Let us have these equations. There is another equation we have seen, that is V equal to open circuit voltage minus open circuit voltage divided by short circuit current into I. It is the value of the simplified one. This is the equation 2 already we have seen, that is simplified. Now let us substitute the values. V1 equal to open circuit voltage is given as 80 voltage, whereas short circuit current is given as 800, and the corresponding I value is 500. I request one of you, please tell about the value of V1.
30 volts, sir.
So V1 equal to 80 minus 0.1 into 500. We can say it is 30 voltage. Similarly, we have to find out V2. V2 again 80 minus 80 by 800 into 460 is the value. It is 460. So 80 minus 0.1 into 460. V2 value is how much? 34 volts. We are having, now we have found out value of V1 as 30 voltage and value of V2 is 34 voltage. Already we have stated two equations. We can see that already we are having two equations. Now we know the value of V1 here and V2 here and two unknowns. Let us solve these equations. So V1 equal to A plus B L. Let us see that V1 equal to 30 voltage, A is not known and L is 5 millimeter. Okay, this is the equation 1. And similarly, second equation is 34 voltage A plus 7B. Okay, these are the two equations we have to solve. Two equation, two unknowns we have to solve. Let us subtract equation 2 and 1, and we are having 4 in the left hand side. A will be cancelled. There is a 2B. So value of B equal to 2. Substituting this B equal to 2 in one of the equations, let us say then the first equation. So 30 equal to A is not known, B value is 2, and value of the arc length is 5. So totally A plus 10 and value of A equal to 20. Now we have found the value of A as 20 and B already we have found 2. Now we have to form the equation using this generic equation. V is here, it is termed as E as per the problem given. It is the linear voltage E equal to A value is 20, A value is 20 plus B equal to 2 and 2 into L. So this relationship is asked. Now we have found out the relationship. This is the answer for the first problem. Let us see the one more problem. The problem is given as in an arc welding process, the voltage and current are 25 voltage and 300 amperes respectively. The arc heat transfer efficiency is 0.85 and the welding speed is 8 millimeter per second. The net heat input in joules per mm is asked. Okay, this is the arc welding process. Let us consider shielded metal arc welding process. Okay, and we are joining two workpieces like this, and this is the welding cross section, and welding is done along the length of the workpiece. The given value are the voltage is V equal to 25 voltage and current is 300 ampere. Now we have to understand the efficiency involved in the welding process. Let us say we are using the transformer as a welding machine. We are plugging it into the power source in the plug point. So we are giving the 25 voltage and 300 amperes to the welding machine. Okay. Let us say that it is heat generated. Let us say it is a heat generated. It is the plug point in which we are tapping the electric power that will give the 25 voltage and 300 ampere using the transformer. Okay. Now this is called a heat generated. After that the arc is generated. Okay, using this heat or power source we are generating the electric arc in the electrode. Okay, now electric arc is generated. Now heat is given to the workpiece. During the generation of the electric arc, the entire heat source is not transferred to the workpiece. There will be some loss. This is termed as a heat transfer efficiency. Let us say this is a heat transfer efficiency or heat supplied. Okay, heat supplied. Heat supplied. That is, it is a efficiency of the heat transfer. So heat generated will be there. There is a loss and heat supplied will be there, accounting the heat transfer efficiency. Again, when the heat is supplied to the workpieces, there is a loss of a heat again, dissipation among the workpiece and loss into the environment. Because of that, the heat supplied to the workpiece and heat used for melting the workpiece will also reduced. So let us say it is the efficiency for the melting. So finally we will get heat required. Heat required to melt. There is a loss in between melting efficiency and heat supply will be there, accounting the efficiency of heat transfer, and finally it's a heat generated. So these terms and efficiencies we have to remember while solving problems like this. In the given problem, let us say it is a heat generated. Let us draw this line for better understanding, and heat supplied and heat required. In this problem, the 25 voltage and 300 ampere is the input power. Okay, the heat generated we can calculate. 25 into 300 will be the heat generated. The value will be 7500 joules per second. This is the heat generated at the power source. Then there is a heat transfer efficiency is given. Heat transfer efficiency is given, that is called 0.85 or 85%. Now we can calculate heat generated or heat supplied, that is 7500 multiplied with 0.85, which is the heat transfer efficiency. The heat supplied will be 6375 joules per second. So this is the heat supplied. Now we have to calculate the heat input in joules per millimeter. Joules per millimeter we have to calculate. Now the problem asks only what is the heat supplied. We need not to worry about heat required, or we can say the efficiency is 100%. So the heat supplied equal to heat required. It's a assumption only. We have to calculate the heat input in the joules per millimeter. These are all the two pieces of metal to be joined, and this is the welding speed. Let us say welding is done along the length of the workpiece. So welding is done like this. It is called a welding speed, and unit of the welding speed we can say millimeter per second or millimeter per minute or meter per second or minute, like that we can specify. Here let us say the welding speed will be in millimeter per second. Now the output requirement, my requirement is what is the heat input, per millimeter, that is requirement. But I am having a value of 6375 joules per second. Okay, so now I have to divide this with the welding speed, that is millimeter per second. So the seconds will cancel. I will get a value of the heat input in terms of joules per millimeter, whereas the welding speed is given as 8 millimeter per second. 6375 divided by 8 millimeter per second. What is the value?
635 joules.
635 joules per millimeter. So this is the value which I require in terms of joules per millimeter. So this is the heat input. Let us see one more problem. In arc welding of a butt joint, the welding speed is to be selected such that highest cooling rate is achieved. Melting efficiency and heat transfer efficiency are 0.5 and 0.7 respectively. The area of the weld cross section is 5 mm square and the unit energy required to melt the metal is 10 joules per mm cube. If the welding power is 2 kilowatt, the welding speed in millimeter per second is closest to watt. The required parameter is what is the optimum welding speed in millimeter per second is asked. Let us use the available data for better understanding. Let us draw this a line. This is the heat generated and this is heat required and heat supplied. Here the efficiencies are given. Melting efficiency is 50% and heat transfer efficiency is 70%, that is 0.5 and 0.7. Here the heat generated is directly given in the problem, that is 2 kilowatt. Now let us come to the heat requirement by using the efficiencies. Let us calculate the total heat required is 2 kilowatt. Let us have it in watts, 2000 watts multiplied by 0.7 and multiplied by 0.5. We will get a power. What is the value we are getting? 2000.
700 joules per second.
700 joules per second. Now the heat required is 700 joules per second. Now we have to calculate what is the welding speed in millimeter per second. Let us use the other details given in the problem. The 700 joules per second is equal to, how to get it? The area of cross section is given. Area of cross section of the welding is given as 5 mm square. Let us consider these are all the two plates we have to join and edge preparation has already done and this area is given, that is 5 mm square. Now the energy required or heat energy required to melt 1 millimeter cube is 10 joules. Let us say 10 joules per mm cube is there, 10 joules per mm cube. Then what is the total energy required? Let us say we have to multiply this volume of the weld. Here the cross sectional area is known 5 millimeter square and there is a welding speed here. There is a welding speed, let us say millimeter per second. So let us say this is welding speed. Let us say S is in terms of millimeter per second. Now we are having both sides 700 joules per second and also right hand side the heat required to melt the metals per mm cube, it is 10 joules. Total volume, if you multiply, you will get a total energy. Here I want to find out S, that is the welding speed, 700 divided by 10 into 5. The value is about 14 millimeter per second. This is the answer. For the given details, we have to have a welding speed in the rate of 14 millimeter per second. That's all about the problems today. Today we have discussed about what is a definition for the metal joining process or welding process. After that we have seen the classification of welding process in brief, and we discussed about what is a fusion welding process, and we have solved 3 numerical problems related to fusion welding process. I thank all of you for listening this video. Let us see the problems in spot welding in a similar session later. Thank you.